Electronic configuration is the arrangement of electrons around the nucleus of an atom in order of increasing energy. Okay? All right. Please put down. Elements in the same group have same outer shell electron configuration. Elements in the same group have same outer shell electron configuration. All right. So these are the three rules. So you must actually know these rules offhand, just in case. All right. So let's look at the first one. Now, let me just explain each of them before I give us definition. Now, this Aufbau rule is telling us that when filling electrons into orbitals, electrons must enter the orbitals of lower energy first, completely, right? Before moving to a higher one. That means if I'm filling one S2, you cannot have one S1 and jump to 2S. S can take maximum of how many? So before I leave these two, before I move away from 1S and move to the next one, this guy must have gotten how many? That's what it means. When filling electrons into an orbital, electron must occupy first the orbitals of the lower energy before occupying orbitals of what? Higher energy. All right. Now, Hund's rule, the second guy is Hund's rule. Now, this guy says that for degenerate orbitals are the p and the d orbitals. Degenerate simply means they spell degenerate. Now, these are orbitals of same energy. P orbital has 3 suborbitals. 1, 2, 3. While D has 5 suborbitals. Now, what this is trying to tell us is that since both this is P orbital, which is this is Px, Py, and Pz, they are all the same energy. They have the same energy. So when you're filling electrons here, electrons enter singly first before what? Pairing. So it means that for this guy to have 2, this must have gotten at least 1, 1. You cannot come and give this guy 2 when one of these have not gotten 1. So Hund's rule says that when filling electrons into degenerate orbitals, electron enters singly first before what? Pairing. Now, what of Pauli exclusion principle? This guy says that no 2 electrons in the same orbital will have the same 4 values or the same values for all the 4 quantum numbers. No 2 electrons in an orbital will have the same value for all the 4 quantum numbers. Now, when I treated quantum numbers, I stated that spin in an orbital, a box like this, you can never see 2 electrons pointing the same direction. One will point up and the other one will do what? Point down. So spin of 2 electrons in an orbital must be opposite. Now, the four quantum numbers that we have are the principal. We have the principal, azimuthal, the magnetic, and the spin. Now, it's possible for 2 electrons in the same orbital to have the same n. That's the same principal. Right? It's possible for them to have the same what? L. It's possible for them to have the same what? ML. But it can never be possible for them to have what? One of them will have plus half, and the other guy will have what? Minus half. So that is basically what this guy is telling me. So let's now define these guys so that I can jot it down. Please put down. Aufbau principle or Aufbau rule states that when filling electrons into an atomic orbital, electrons must occupy completely the orbitals of the lowest energy level before occupying orbitals of the higher energy level. States that when filling electrons into an atomic orbitals, electrons must completely occupy the orbitals of the lowest energy level before occupying orbitals of the highest, sorry, not highest, higher energy level. Now, there are a few exceptions to this particular rule. Just in case you're being asked, there are a few exceptions to Aufbau principle. And those exceptions are chromium and copper. Chromium and what? Copper. Now, chromium is 24. Copper is what? 29. Now, if I'm writing electronic configuration for chromium, now look at this. This one S2. Please, pardon me. After that, I'm going to teach us how to write electronic configuration. We have 2S2, 2P6, 3S2, 3P6, 4S. It's supposed to be 4S2, right? Before I move down to, this is how it's supposed to look like. The 3D is presumed to have a higher energy than 4S. So when you're writing it, according to the principle of writing electronic configuration, 3D is always coming after this guy. Now, if you count the number of electrons, here it's 24. This is 2, 4, 10, 12, 18, 20, 24. But the exception here is that this D is going to take one electron from here. Here becomes what? 1, and here becomes what? 5. Remember the rule says, for you to move to a higher energy, you must completely fill the lower energy, right? But this guy did not obey that, right? Now, why is it so? Because this D, or this D being 5, is going to give this atom more stability than this D being 4. So being stable and obeying the rule, this guy actually went with the stability. I repeat. Now, the reason is because when D orbital is half filled or completely filled, the atom actually has extra stability compared to how it was initially. So in a case where this D orbital is 1 electron short of being 5 or 1 electron short of being 10, this guy is going to stretch forth his hand and pick electron from the closest orbital to complete the 5. So this was 2 and this was 4. This is just 1 short of being 5. You see also, it's going to take 1 electron from here. And why is it taking electrons from there? Because if this guy is 5, this guy would be more stable than it was initially, right? So it's now a case of being stable or obeying the rule, right? So this guy actually went with being stable and ignoring the what? The rule. Now, take note of that this is only applicable when the d orbital is 4 or when the d orbital is what? 9. 1 short of being 5 or 1 short of being what? 10. It's not applicable when d is what? It's not applicable when d is 8. Right? It's only applicable when d is 1 short of being d5, like this, or 1 short of being d10, like this now. So in the case of copper, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Once again, this guy is 1 short of being 10. So it's going to take 1 electron from here and put here. This becomes what? D10. So the 2 exceptions to Aufbau principle is chromium and what? Copper. Because the d orbital is more stable when it is d5, that is half filled, or when it is d10, completely filled. So in case somebody asks you, why is it that this guy prefers to be d5 as compared to d4? It's very simple. The atom attains extra stability when it is d5 or when it is what? D10, thereby ignoring the rule. So let's look at Hund's rule. Hund's rule states that for orbitals of same energy, in bracket, degenerate orbitals, electrons enter singly first before pairing. Electrons enter singly first before pairing. Singly first before pairing. Electron enters singly first before pairing. Now, please, what are the examples of the degenerate orbitals? P orbitals are degenerate. P orbital has 3 suborbitals. Now, this is how it looks like. If I have these 3 orbitals, and let's say I have 5 electrons to fill into this guy, you have to put one single first, 1, 1, and 1. Why? Because 3 of them, they are all of the same energy. Now, once you're done 3, how many is remaining now? 2. You now start pairing. This guy will not be angry because the electron did not get to its part, but this would have been very upset if you had put 2 here without giving this guy 1, right? So before any of them holds 2 electrons, 3 of them must have gotten at least how many? 1. So p orbital has 3 suborbitals. Now the next degenerate orbitals is d orbital. D orbital has 5 suborbitals. One, two, three, four, 5. So let's assume I have 7 electrons to fill into this orbital. This will go first. 1, 2, 3, 4, and 5. Singly first. Then to come back 6 and what? 7. So these two, F orbital is also degenerate, but it's more like more advanced than this level. So these are the two degenerate orbital. S is not degenerate. S is just a single box. This guy is not degenerate. S is just a single box. So here you can have 1, 2, right? But for P and for D, for anyone to be paired, 3 of them at least must have 1 electrons each. Same thing for D. Please put down. This states that no 2 electrons in an orbital will have the same values for all the 4 quantum numbers. Comma. The spin must be different. The spin must be different or opposite. Now let me explain this particular guy just like I explained the first one and this guy. Now let me explain something. In quantum numbers, we have 4 types of quantum numbers. We have the principal, which has a symbol of N. We have the azimuthal, which has the symbol of L. We have the magnetic, which has the symbol of ML. And we have the spin. Now let's assume, for example, I have 1s2. All right, I want to start writing electronic configuration. And the first one is 1s2, meaning that the first 2 electrons here are inside this box. Please look up. I said I want to explain this now. This rule is telling me that no 2 electrons, an orbital basically is a small box in an atom. So maybe in exams they ask you, what is an orbital? An orbital is a region in an atom where electron resides. Now look at this. 1s2. This guy has 2 electrons. I come here, I put this and I put this. If I want to get the quantum numbers for this guy, class, these 2 electrons, they will have N. The first value, N, is always this number here, right? Both of them will have principal quantum number of how many? 1, because they belong to the first shell, is it not so? Both of them are inside S orbital. And according to azimuthal, S has a value of 0. Remember, SPDF, azimuthal gave it L to be equal to what? 0, 1, 2, and what? 3. Please, if you missed out the video for quantum number, I think we have video for quantum number. Right? I've treated quantum number, but I'm still going to treat it again. So this one here is the 2 electrons have the value of 1, is it not so? Because both of them are inside S orbital that is present in the first shell. The 2 of them are inside S orbital. And what is the value of S orbital for azimuthal? 0. So both of them will have L equals to 0. Class, remember, once L equals to 0, what did I tell us? Once L equals to 0, ML will be 0 automatically, right? So this becomes ML equals to 0. So you can see that it's possible for 2 electrons in an atom to have same values for the principal, azimuthal, and what? Magnetic. This one that is pointing up has N1 equals to this, L equals to this, ML equals to this. You know so. The one pointing down is also having the same values, right? But guess what? Their spin can never be the same. The one pointing up, upward spin is always what? Plus half. Downward spin is always what? So this is actually where the difference comes in. So it is wrong for me to say this. It is wrong for me to say this. But it is right for me to say. So in case you're wondering, where are we going to use all of this? Now, there are various ways to write electronic configuration. We have the SPDF notation, which is the ones many of us are familiar with. 1s2, 2s2, is it not so? Have you heard of orbital box diagram? Where you have something like this. You have, I think in secondary school, something like this. Have you seen something like this? The first energy level 1 can only hold S orbital. That's why you can see S here. Energy level 2, that's the second shell. These numbers represent the shell of an atom. Periodic table has 7 periods, which means the highest number of shells of electron you're going to see is 7. That's why we are stopping at 7. Now, first shell can only hold s orbital. That's why the element in the first period has just one shell, hydrogen and helium. That's why they just have one shell, right? Second shell will only have s and p orbital. Third shell will have s, p, and what? D. Fourth shell will have s, p, d, and f. Is it not so? Now, how do you write electronic configuration? If you want to fill electrons, how do you fill it? Like this. You take the s first. After this guy, you move down to 2s. From 2s, you go like this. So after 2s, you go down to 2p. After 2p is what? 3s. After 3s is what? 3p and what? So that's the order of writing electronic configuration. So here, you write 1s first. That means when you're filling electron, that's why we say order of filling electron. You fill electron first in the 1s, after which you move down to what? 2s. From 2s, you move down to what? 2p. From 2p, 3s, 3p, 4s, 3d, 4p, 5s. 5s, after 5s, you have what? 4d, 5p. So that's how it is. After 5d, yeah. Sorry. Please, this is 6p. Please, this is 6p. Sorry, thank you. 4d, 5s, 6s. So that is how we write electronic configuration, right? Now, note, when filling electron, s orbitals, and maximum number of electrons they can hold. S orbital can hold maximum of 2 electrons. P orbital can hold maximum of 6 electrons. D orbital can hold maximum of 10. F orbital can hold maximum of 14. That means when you're filling electrons, you cannot put more than 2 on the S. S can hold 1, yes, but the highest number that S orbital can take is 2. P, the highest number P can take is 6. P can hold 1, P can hold 2, P can hold 3, up till 6. D can hold 1, D can hold 2, up till how many? 10. F can hold up to how many? 14. So that is that for that. Now let's look at this example. If you're writing electronic configuration for a neutral atom, how do we go about it? If you're writing that of a charged atom, how do we go about it? So we have, give the electron configuration of the following. So we have the first one, Na. We have the second guy, Na plus. We have the second guy, Ca. Now look at this. We have an atom and an ion. You know, most times I've seen a lot of persons, whenever they want to write electronic configuration of an ion, they'll first of all calculate for number of electrons. Well, that might be correct as well, but then I don't want us to follow that pattern. So let's use scandium, and let's use scandium ion. Now, if you want to write electronic configuration, what the first thing you should look out for is the atomic number of that atom. The atomic number of that atom will give you an idea of the number of electrons present. Because for every atom, the atomic number is always the same thing as the electron number. When an electron is being removed, you're going to do the same thing from the electronic configuration. Don't subtract the electron before you start writing the electronic configuration. It might work in some, it might not work in some. All right? So like I said, I always prefer something to be systematic. So we have these few examples. Of course, I'm not going to do all of them. I'm just going to choose some few ones, and then that is it. So let's start. For the first one, Na. Please pay attention and look up. This guy has atomic number of 11. If I want to write electronic configuration for this, I already gave us an order in which we are going to follow. We're going to start with 1s. From 1s, you move down to this. So this is going to be 1s, 2. I've used 2 electrons from here. 2s, 2, because after 1s is 2s. Now, 4 electrons have been used, remaining 7. You have 2p what? 6. You have 3s what? 1. Now, for the ion, please look up. Please, plus simply means that electron has been what? Removed. Electron has been what? Class. For you to write this, I will always advise you first of all write that of the neutral atom before you write that of the ion. I will explain. This is sodium ion and this is sodium atom. Is it not so? You cannot have this without having this. Ion cannot exist if the atom is not in existence already. Right? So whenever you're writing an electronic configuration for that of ion, even if you're not writing out this one for people to see, you can actually just write this guy at the cover or the side of your note. So this is what is going to happen. Class, plus means, does plus means addition of electrons or removal of electrons? Now, no class today. If you want to remove electrons from an atom, class, do you remove electrons from the outermost shell or from the innermost shell? Obviously, because you cannot come somewhere and start going inside. You remove from the what? And from electronic configuration, how can we tell which of the shell is the outermost shell? Class, look up. The outermost shell is the shell with the highest number. The shell with the what? This guy, 1, this is the first shell, right? 2, the second shell, is it also? 3 is a third shell. That means this atom has how many shells? 3 shells. And the outermost shell is a what? 3. So, plus means removal of how many electrons? 1. We are going to remove the electron from the outermost shell, which is what? These 3. If you remove 1 electron from here, this guy becomes 0, is it not so? So this becomes 1s what? That is it. Because a lot of persons will first of all calculate the electrons and start adding it. It will work in some, but if you're doing that for transition metals, you fail it. It's a must. All right. So that is that for the first one. I'll clean this to do the second guy. So look up. For the second guy, we have calcium 20. What's the atomic number of this guy? 20. So we start. 1s2. 1s2. We have used 2 electrons. 2s2. 2p6. 3s2. 3p6. What? That is it. Electron is 2, 4, 10, 12, 18, 20. Now, if you want to do that of calcium 2 plus, guys, 2 plus means electron has been lost, right? How many electrons? 2. Please, the 2 electrons will be removed from the outermost shell. Is it not so? And what will be the outermost shell? Shell with the highest energy. And which of them is the highest energy here? 4s. It means that this atom has 4 shells. The first shell, the second shell, the third shell, and the fourth shell. So if you're removing electrons, you remove from the outermost shell. And plus 2 means removal of 2 electrons, right? So if you remove 2 electrons from here, this guy becomes 1s2, 2s2, 2p6, 3s2. Please look up. Now, chlorine has 17. This is 1s2, 2s2, 2p6. This is 10 already, right? 3s2, 3p what? 5. Now, for this guy, please, minus means, does it mean addition or subtraction? Minus means electrons has been added, right? How many electrons is added here? 1. So now look up. The question is, where are you going to add the 1 electrons? Very simple. If the electrons was removed from the outermost shell, if you want to add, you see add to the what? Outermost shell. How many shells does this atom have? 3 shells. How can you tell that? The numbers here. The highest number is what? 3. Please look up. This guy is going to be 1s2, 2s2, 2p6, 3s2. Please hold on. I want to do this. The outermost shell is 3. The third shell is not so. The third shell is repeating how many times here? 2 times. 3s and what? The s has gotten maximum number of electrons, which is how many? 2. Remember, s can take maximum of 2, is not so? So if you want to add, you cannot add to s again. P can take maximum of how many? 6. How many is P holding here? So that means this P can still accept 1, is it not so? So this guy becomes what? 6. So this becomes the configuration of the ion. Scandium is 21. I believe by now, many of us will know how to write this. Please, 21, just follow this pattern. All I just want you to do is, if you can actually get this pattern, 1s, put s, energy level 2 can hold 2s and 2p, energy level 3 can hold up to d, 4 can hold up to f. So we start here, we have 21 electrons, so we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Now, I will tell you the reason why I used to tell students not to always count the electron first. Imagine if you had a lot of persons who first of all calculate the number of electrons before filling. Nope. Class, you cannot write electronic configuration of an ion without knowing that of the atom. Like I said previously, ions do not exist on their own. They exist as a result of an atom losing or gaining what? Electron. So adopt that as well. Class, scandium 3+. How many electrons have this guy lost? Now the question is, the electrons has to be removed from the outermost shell first. Is it not so? Now, look at this guy. What is the outermost shell of this atom? Shell number what? 3d1 is wrong. Because the number of shells, look at these numbers. What is the highest number you can see here? 4. Understand what this atom has? How many shells, class? For you to know from electronic configuration, you can tell how many shells an atom would have by just looking at these numbers. The highest number here represents the shell, the highest shell. The highest number in this case is what? That means this atom has how many shells? 4 shells. And the 4th shell is the outermost, right? So, if I want to write the electronic configuration for this guy, the outermost shell, which is the 4th shell, right, has how many electrons here? 2. If you remove 2 electrons from here, is it still up to 3? That means, after removing from here, which one will come next? 3D. So imagine it was a case of, imagine this thing was like this. Some person would have just removed from this D. Do you know if you remove from this D first, you fail it? Hello? If this thing is like this, and you come here and do this, just remove this D, do you know you failed that question? Because you're meant to remove electron from the outermost what? Shell. And how do you tell the outermost shell? From the electronic configuration, the shell with the highest number. And which of them has the highest number here? 4. So if you want to start removing electrons, or if you must remove electrons, it must be from the what? From the 4. So if we have 3 here. So after removing 2 from here, that is now when you start looking at the what? The D. So this becomes 1s2, 2s2, 2p6, 3s2, 3p what? 6. This guy, if you remove the 2 electrons, it becomes 4s0, is it not so? Remove 1, it becomes 3d0, is it not so? So this becomes the electronic configuration of this guy. So take note of that. Now we have a shorthand way in which we can write electronic configuration. They may not have taught you guys this yet, but I just feel it's very, very important for us to understand how to do this, so that in case of exams, I don't want to leave any stone unturned. Now, have you ever seen, you go online to check for electronic configuration, you see something like this? Have you seen something like this before? Now, this is writing electronic configuration in terms of the noble gas. In other words, this is the shorthand way to write electronic configuration. So first thing first, since we are writing this guy in terms of the noble gas, it is important for us to know the various noble gases that we have. The first member of the noble gas, we have helium, which has atomic number of 2. We have neon, which has atomic number of 10. We have argon, which has atomic number of 18. We have xenon, which has atomic number of 54. So let's start with this. Let's stop here first. So if you're asked, please listen and stop writing. If you're asked to give the shorthand method, or you're asked to write electronic configuration of sodium in terms of the noble gas, listen how this question can be asked. They can ask to write electronic configuration of sodium in terms of the noble gas, number 1, or to write the shorthand electronic configuration of sodium. Shorthand or short form, whatever. So this is what we're going to do. Please look up. If I have, for example, I just want to use an illustration to explain this, because talking plenty is going to be taking our time. Sodium, for example, is 11. Electronic configuration of sodium normally is 1s2, 2s2, 2p6, 3s what? 1. Is it not so? Class, which noble gas comes immediately before sodium? Neon. It means that you're going to write this sodium in terms of neon, because neon is 10 and sodium is what? If you're asked to write in terms of noble gas, you're always going to choose the noble gas that is coming immediately before the atom in question. Are you getting me? Immediately the atom in what? Question. Now, assuming they asked me to write that of calcium. Calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s what? Which noble gas comes immediately before calcium? Argon. Argon is 18, right? After 18, 19, you have what? 20. Now, this is what you're going to the class. Look up. Please stop writing. Imagine I'm asked to write electronic configuration of sodium in terms of the noble gas, or I'm asked to write the shorthand form of this guy. Shorthand means in terms of the noble gas. This is what we're going to do. First thing first, these are the noble gases that we have. Class, which noble gas comes before sodium? Neon. What is the atomic number of neon? Count 10 electrons here. This is 2, right? This is 4, and this is what? So this guy, if you write electronic configuration of neon, this is what you're going to have. So instead of writing this guy as a whole, I'll just come here and say what? Neon. Because once I see this and this is the same. Neon has 10, is it not so? If I'm to write electronic configuration of neon, this is what I'm going to have. Right? So I'll ask myself, sodium is 11. Which noble gas comes before sodium? Neon, right? So I'll count 10 electrons from here. So instead of writing this guy, I'll put what? Neon. And then I'll complete it as what? 3s1. So this becomes electronic configuration of sodium in terms of the noble gas, or the shorthand form. Calcium. Which noble gas comes before calcium? Argon is how many? Count 18 electrons from here. 2, 4, 10, 12, 18. So it means that everything here will be replaced with what? Argon, and then I balance what? Does it make sense? Okay, please, another way they can call this guy is condensed electron configuration, or condensed form. Please take note of the name. There are different names. They can call it in terms of the noble gas, or the condensed electronic configuration, or the shorthand form. All right, you can see that this is it. I am asked to give the electronic configuration of vanadium in terms of the noble gas or the condensed form. Now, normal electronic configuration of vanadium is 1s2, 2s2, 2p6. Now, this is 10, 3p6, 4s2, 3d2. Now, this is 22. Now, the next thing I'm going to ask myself would be, which noble gas comes before 22? It's argon. Argon is 18, right? So come to this guy, count 18 out. 2, 4, 10, 12, 18. So if I count this guy out, so everything here becomes argon. And then I'll complete this guy. This becomes 4s to what? Class, with this pattern, any type of atom they give to you guys, just try and adopt on. Make sure you understand this. If you understand this, I don't have to solve 50 examples. If you understand this, I'm very certain that any question you come across, you're going to smash it. So these are the three major applications of electronic configuration. Now, with electronic configuration, one can tell the period of an element, one can tell the block, and one can tell the group. So I'll start with the period. I said the period of an element, first of all, I told us that periodic table has 7 periods of elements. Period 1, period 2, period 3 till 7. When we treated periodic table, I characterized each of those periods, telling us the number of elements that can be present in a particular period. Now, with just electronic configuration, you can tell the period of that element. Like I said, the period of an element corresponds to the highest energy level in the electronic configuration. Example, if I have something like this, 1s2, 2s2, 2p6, 3s1. Class, what is the highest energy level in this guy? The energy levels are these numbers you're seeing here, right? What is the highest number you can see here? That means this guy belongs to period what? 3. So this guy belongs to period 3 because the highest energy level here is what? 3. Now, if I have something like 1s2, 2s2, 2p3, what is the highest number here? Now, 2 is repeating or is appearing 2 times, right? It doesn't really matter. As long as there is 2 here being the highest. This guy belongs to period what? 2. So this is period 2. Now, the last example before we look at something else, you have 1s2, 2p6, 3s2, 3p6, 4s2. What is the highest energy level present here? 4. Of course, this is the 4. So that means this guy belongs to period what? Period 4. So that is how, with just electronic configuration, you can tell the period of an element, live and direct. No stress. So the next one is determination of what? Determination of block of elements. Now, another application of electronic configuration, by just writing electronic configuration, you can tell the block of that element in the periodic table. Right? Now, please put down. Periodic table has 4 blocks of elements. Periodic table has 4 blocks of elements, namely the S block, the P block, the D block, and the F block. With electronic configuration, the block of an element can be determined. With electronic configuration, the block of an element can be determined. Determination of blocks of elements. First, we have 4 blocks of elements. We need to establish that fact. And I went ahead to tell us that with electronic configuration, the block of an element can be determined, which I proceeded to say the block of an element corresponds to the type of orbitals which receives the last electrons in the electronic configuration. The block of an element corresponds to the type of orbital which receives the last electrons in electronic configuration. Now, this is very simple. It means that if you're writing an electronic configuration, let's say, for example, I have 1s2, 2s2, 2p6. I have the next one, 1s2, 2s2, 2p6, 3s1. Class, look up. Now, in this first case, now the last electron here entered which orbital? P orbital, right? It means since the last electron entered P orbital, this electronic configuration belongs to an element under which block? P block. That's what it means. In this case, now the last electron entered where? S. So it means that this element belongs to which block of elements? S block. So let's say I have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Class, what is the block of this element? Where did the last electron enter? It's D now. So that means this guy is in D orbital. Because the last electron entered where? D. So therefore, if you go through your past questions, you see a case whereby they'll give you electronic configuration or they give you X. They can give you something like this. They just give you the atomic number like 17. And you're going to be asked, or they can just give you something that is higher than the first 20 elements, because they know if they should give you 17, you know that 17 is for chlorine. They can give you 45, which if I should ask us which element has 45, many of us will not be able to recall, or perhaps many of us are not aware of. Yes? So they will ask you, X has 45 atomic number. What is a group of X? What is a group number of X? What is the period of X? And perhaps what is a block of X? Now you might be wondering, how can I actually get the group of an element, the period of an element, as well as the block by just the atomic number? It's very simple. If you know how to write the electronic configuration, which I showed us yesterday, once you've succeeded in writing the electronic configuration, from there, you can get the block of the elements. We have 4 blocks of elements. We have the S, P, D, and F. I told us how to identify the block of an element. Still from the electronic configuration, you can tell the period, right? The group was what, we couldn't actually cover yesterday because of time. So that's basically what we want to do now. Now, class, before you actually be able to get the group of an element using the electronic configuration, listen. You must first of all identify which block that element is actually present in. The pattern or the method I'm going to use for S block elements is going to be different from the one I'm going to use for P block. It's also going to be different from the one I'm going to use for F block. So once they give you an atomic number or perhaps the electronic configuration and you ask for the block, very simple. First, the group. Which block of elements is that guy? If it is S block, there is a pattern or a formula you can use to get that of S block. If it is P block, there is a formula. So having said that, we'll just dive into this proper. So do not forget that we have 2 ways of numbering elements in the periodic table. We have the IUPAC way of numbering, and we have the CAS, which I taught us. So if you're asked for the group, most of the times they can specify, give us in IUPAC or give us in the American. But if they don't specify, any one of them you give to them, they will still mark you correct. So for the CAS/America, now let's look at this. For the IUPAC, the group number would be number of electrons on the valence shell. Remember, valence shell is same thing as outermost shell. Remember I said periodic table can be numbered either following the IUPAC method or the CAS. So if you're going through the IUPAC method, this is how to get your group number. Just locate the valence shell. From the electronic configuration, the shell of the highest energy level. How many electrons is actually on that shell? If it is 2, that means that guy is in group 2. If it is 1, that means we have that guy in group 1. Now for this guy, Now we have this. So I'll use one side of the board to do that, to do the example. I don't want to clean this. So for S block element, remember I said if you're asked to give the group of an element, first check whether that guy is in S block. I'm going to show us that now. Let's say, for example, I have an element has electronic configuration 1s2, 2s2, 2p6, 3s1. Now look at this. I told us yesterday that for you to be able to identify which block of an element that a particular element would be, it is the orbital that receives the last electron. Now, when you're writing this electronic configuration, it means that whichever atom that has this has 11 electrons, which is atomic number of 11. This is 2, 4, 10, and 1. The 11th electron, which is the last electron, entered S. So the orbital that received the last electrons obviously determine the block of that element. If the last electron entered P, it would have been P orbital. But the last electron entered S. So this is S orbital. So the pattern I'm going to use for S orbital, which is S block element, would be, according to the IUPAC, my group number equals the number of electrons on the valence shell. According to the CAS, number of electrons on the valence shell attached with what? A. Shut up. So from here now, class, is this guy S block or P block? Because the last electron entered where? S orbital. So the group number of this guy, according to IUPAC, would be, what is the valence shell? Valence shell is the shell of the highest energy level, isn't it also? So in this electronic configuration, which of this number is the highest? 3. I'm looking at this number 1, we have 2 here, we have 3, isn't it also? How many electrons is on this 3? 1. So this guy is group what? 1. According to CAS, this guy would be group what? 1A. That is it. Most of the times, please, this CAS always use Roman, is it Roman figure? Roman is figure bar. So instead of me to say 1, I can simply say what? IA. That's that for S block. So first of all, check if that guy is in S block. If it is in S block, there is a pattern for S block. Group number equals the number of electrons on the valence shell / outermost shell. From this electronic configuration, which of this is the outermost shell? Shell of the highest energy level. All right. Let's look at for P block. Now look at this. Now for the P block element, group number according to the IUPAC would be 10 plus sum of electrons on the valence shell. I'll tell us why the 10 is there. For those of us that were in class when we treated periodic table, you realize that we have the D block, which is at the center of the periodic table, has 10 columns. So for you to get to the P, you have to cross that 10 columns. That is why we have this 10 here. Now, if you're doing the CAS, sum of electrons on the valence shell attached with A. And I'm going to give us an example. Before you actually use this particular pattern, we should ensure that that particular element is in P block. How would you do that? From the electronic configuration, which of the orbital is receiving the last electron? It must be a P that is taking the last electron. So let's look at this example, 3p5. Let's look at this. Class, I don't have to solve 50 examples. Trust me, if you understand just one of these examples, I don't need to solve 5. If I decide to solve second example, it's just for formality. So please look up. Now, first thing first, this guy is a P block because the last electron is entering this P, also. It is a P block, fine and good. The next thing I'm going to do is that, according to IOPAC, I'll say IOPAC, my cars. Cars is same thing as America. Now, I'm going to tell us how questions will come so that you know how to represent this. Now, first thing first, according to the IOPAC, the group number would be whatever the sum of electrons on the valence shell will give us, add 10 to it. Now, first thing first, what is the valence shell? Shell of the highest energy. And how can you tell that from the electronic configuration? The shell that has the highest number. You can see we have 1, we have 2, we have 3, also. The highest number is how many? 3 is appearing how many times? 2. That is why we use the word what? Summation. 3 is appearing here and it's also appearing here, also. So the group number according to IOPAC would be group 10. So let's say this would be group number equals to 10 plus sum the electrons on this guy. What is this guy? Is how many here? How many here? 2 plus 5 is what? That's group what? 17. Now let's do the cars. In this case now we are not adding the what? 10. Just sum of electrons on the valence shell. This is going to be group what? But please, for these cars, always try to use the Roman figures, right? So this is going to be V. Even if you say this, I don't think they'll mark you wrong. Just ensure that you attach the A. So that is how we get that for p orbital. For d block elements, how do you go about it? Please look up. So we said sum of group number. Now this is the IOPAC. Now this is according to the IOPAC. The IOPAC is systematic, but the cars is not systematic, unlike what we did for the previous guys. All right. So this guy, the IOPAC is systematic. For me to get the group number, simply add the electrons of the last 2 orbitals in its electronic configuration. Now let's take an example before I proceed further so that you grab something. So let's say an example, we have 1H2, 2H2, 2P6, 3H2, 3P6, 4H2, 3D2. Recall that from an electronic configuration where the last electron enters, the orbital that received the last electron determines the block of that element. So here, the last electron entered into the d orbital. So obviously, since the last electron stopped at d, it means that guy is a d orbital. Obviously. So now, if you want to get the group number of this guy, we said, according to IOPAC, what is a pattern to get the group number of d block elements? The pattern is very simple, according to the IOPAC. Now, sum of the electrons of the last 2 orbitals in its electronic configuration. The last 2 orbital of this guy is this, isn't it also? Now, how many electrons do we have here? 4. So this becomes group number equals to 2 plus what? That's what? So according to the IOPAC, the elements that have this electronic configuration is in what? Group 4. How IOPAC numbered that guy. So from here now, we said this guy is in group 4. So if you look at this, where is group 4? This is group 4. So this element will be here. And now, the big question now is, how are we going to get the CAS or the American system? Like I said, it's not systematic. Please take note of this. According to CAS, group 12 is 1B. So this part, you need to know it offhand. Group 11 is 1B. Group 12 is what? 2B. Group 3 is 3B. Group 4 is what? Group 5 is what? This is what? This is what? Now look up. Group 8 to group 10 is what? 8b. So how will I know the cars? Is you need to know this. Like this one, you just have to know it offhand. There is no direct formula like the one I gave us for p orbital, like the one I gave us for s. Nope. This one is that you have to know it personally. So looking at this now, we can see that group 4 is sent as 4 bits also. So according to cars here, for this guy, the IO pack would be group 4. So for you to get, listen, in the first case, you don't have to get the IO pack to get the cars, right? For s orbital, you can do the cars independently. For p orbital, you can also do the cars independently, right? But for d orbital, you cannot do the cars independently. You must first of all do the what? IO pack. From the IO pack, you now say, what is the equivalent of group 4 in America? Group 4 is what? 4b. So this is same thing as saying cars will now be group what? So that is it. And we are done with that part. So let's take another example. One last example. What time did I say you guys should remind me to end this part? 5:10. What's the time? Eh? 5:00? Which did I hear 3? Sorry. I didn't mean to react that way. 1H2. Hope you're not shy. I didn't mean to react that way. Sorry. Are you shy? Why are you shy? Please look up. Imagine you're being given something like this to give the group number. Is this guy P block element, D block, or S block? Because the last electron entered into the where? D orbital, sharp. So I'll now say, according to the IO pack, for me to get my group number is basically sum of electrons of the last 2 orbitals in its electronic configuration. The last 2 orbitals in its electronic configuration is this guy. Now, 2 plus 4 is how many? So according to the IO pack, this guy is in what? Group 6, because 2 plus 4 is 6. Now, for me to get the cars, I need to come and say, what is the equivalent of group 6 in B? 6B. Can you see that? Group 6 is same thing as 6B, so that is the answer. So we are done with. For those persons that missed out periodic table class, please try not to miss out the second class, which will commence sometime next week. So we are done with everything about electronic configuration. Done and dusted.